Okay, thank you. It's a great pleasure to be here. It's a very nice conference. This talk will be about verified numerics for ODEs in Isabelle. First of all, why ODEs? So they're a very useful model for modeling physics or biology or dynamical systems. And so you basically you can describe forces that act on something in a state space. Often there's no closed form solution for an ODE, which is why one usually resorts to numerical algorithms and, so to say, simulates what the ODE does. There, we usually have, or most numerical algorithms are usually approximate, so they discretize the solution, for example, in a series of linear approximations to the solution. And now, if you're just a little bit paranoid, you may not be satisfied with having some result which is just close to the solution, because often you know that this approximation is close, but that's just some O of something, and you want to have guarantees. That's why we concentrate on what I call rigorous numerical algorithms for solving ODEs. There we compute enclosures, which means we're not going to compute values which are close to the solution, but some set-based representation which is guaranteed to enclose the solution. Now, if you're, again, a bit more paranoid, you can ask yourself, what about these enclosures that I computed? Are they actually correct? Did I make some mistakes in the algorithm that I implemented in the program or whatnot? So that's why we aim for verification of such rigorous numerical algorithms. And we do that in an interactive theorem prover, Isabelle, in the logic HOL. And for this, so the basis of all this is a formalization of real numbers or vectors of real numbers and ODEs, which are formalized, specified in the theorem prover. And based on this, we verify numerical algorithms, rigorous numerical algorithms. These algorithms are, so if you want to verify an algorithm, it's much easier when you specify the algorithm as abstractly as possible. So in this case, we want to formalize or specify the algorithms in terms of real numbers and not floating point numbers. So the verification is done in terms of real numbers, and then we use this abstract specification and refine it towards something that can actually be computed, like finite precision floating point numbers. And from this executable specification, we generate code, and you get quite high guarantees on regard to the level of trust that you can put into the code that you obtain after this process. So what are we going to do with the code once we obtained it? We're going to run it on some examples, and there we faced some challenges, and I want to report a bit on what challenges there were and how we solved them. So one example was the Euler reservoir problem, which is a stiff ODE, which poses some problems. The Van-der-Pol system, which you've seen earlier during the conference, it's a nonlinear ODE, and that poses problems. And like the main or flagship application of the approach that I'm going to present is the computations on the Lorenz Attractor. There, the situation is that there exists a proof on some topological properties of this Lorenz Attractor, this structure. And this proof is based on some estimations that have been obtained via a numerical program. And so the situation is that if you want to trust the proof, you have to trust the program, which up to now has not been verified. But the algorithms that I present here are verified, and we can use them for the same kind of computations. So now I'd like to go a bit more into detail. First about what the basis of the formalization is and how we verified our programs. So some general background. So we use Isabelle with the logic HOL as a theorem prover. It's an interactive theorem prover implementing higher order logic. That means higher order logic, you can see it as a functional programming language in which we're going to specify our programs, but it's also equipped with logic, so you can do some reasoning. When I talk about formalization, I basically mean the definition of concepts and stating some properties about those concepts. Like concept could be real numbers and properties that addition on real numbers is commutative. And when I talk about verification, I mean proving those properties in the proof assistant. That means all the proofs are really reduced to their the basic inference steps, which is guaranteed by the kernel of the proof assistant. And so all the proofs are machine checked and means you can really trust them. Now a bit more specific about the way mathematics is formalized in Isabelle. So basically everything is constructed from first principles. So you can think of it as starting from natural numbers, you construct integers, where if you take quotients, you get the rational numbers, and there's some completion of Cauchy sequences or something. You can construct the real numbers. Building on top of that, we have access to a quite good library of multivariate analysis, which has originally been ported from John Harrison's developments in relied. And there we get things like Taylor series expansions or the Banach fixed point theorem, which is particularly important for ODEs. But since Harrison's developments have been ported, they have been generalized to a larger extent because we chose in Isabelle to have most of the formalization based on type classes, because we have axiomatic type classes. That means, for example, we have a type class for metric spaces, where you choose as a parameter a distance function, and they're axiomatic because you can also assume some properties about these about the parameters, so that here in this case equal elements have to have distance 0 and the triangle equality needs to hold. And so the nice thing about having these type classes is that you can do all the reasoning, which basically only requires axioms from metric spaces. can be done generically in terms of the type class. So consider the Banach fixed point theorem in Harrison's developments. It's really just formalized for the fixed type of vectors of real numbers, whereas in our case we can state and prove it just generically for metric spaces. And then we can instantiate types to be an instance of the type class. So we can say that real numbers are a metric space or complex numbers are a metric space, and then you can immediately use all the results that you've proven generically for metric spaces. You can use them for real numbers, complex numbers. Coming to how we formalized ODEs in Isabelle. So we look at, in this case, autonomous ODEs, where the derivative of some unknown function psi is given by some right-hand side, which may depend on the value of psi at that time. And usually an ODE is equipped with an initial condition. That means at time 0, you have to start at a value 0. So the first thing you want to formalize when you talk about ODEs is the existence of a unique solution, which is given under relatively mild assumptions. It's known as the Picard-Lindelöf theorem. When you look into a mathematics textbook, the Picard-Lindelöf theorem usually works with the so-called Picard operator, which works on the space of continuous functions from a compact interval to, say, Euclidean space. And it's defined as the mapping from some function to basically the antiderivative of the ODE. And so with this definition, we have this Picard operator P. It operates on a function space. And on this function space, you usually want to apply the Banach fixed point theorem, which guarantees that there's a unique fixed point, which is then a unique solution of the ODE. Now, if we wanted to do this directly in Isabelle, this doesn't work because, unlike Coq, we don't have dependent types. And you see that this function space here, the domain of the functions, this compact interval from T0 to T1, so this type depends on T0 and T1, so it's a dependent type. So you can't really use it. And that's a bit of a peculiarity where you need to be a bit creative in the formalization if you want to cast it to a language where you don't have dependent types. And in this case, it was rather easy because we just worked with a type of bounded continuous functions, which are total, means defined on whole R, and are bounded on the whole domain. And this type is like continuous functions on a compact domain. It's also a metric space. So, and it's not dependent. So we can use the Banach fixed point theorem on this type of functions. And so we get the existence of a unique solution, and we're happy. And yes, what else? Often I'm not going to talk about the solution of an ODE with an initial value, or the solution to an initial value problem like it's given here above, but I'm going to talk about the flow, which is the solution starting at some initial value x0 at time t. Okay. So now, up to now, we formalized the abstract theory of ODEs, and but we want to compute numerical approximations to them. So the first step is to formalize a numerical algorithm, or an approximation scheme for that for the solution. And the simplest one that one can come up with is probably the Euler method. And so the Euler method proceeds in a series of steps, and in one step you take as an approximation to the ODE to the solution just a linear function where the slope of that function is given basically by the slope from the ODE at the initial value. That works reasonably well. You get a quadratic error in terms of the step size, and did I want to say? Yes. So you can prove that here you have some quadratic error, which is just comes from the Taylor series expansion, which match up to the second order. And so that's the basis for the classical numerical algorithms that are used. And they just compute this value and have some approximation. And usually you don't really care about this this quadratic term. You just neglect it. As I said in the beginning, here we want to be more rigorous, which is why we work with we extend this Euler method to something which is based on sets or enclosures. So assuming that the initial value x0 is contained in some enclosure which may already contain some uncertainty or errors from previous steps, then the aim is to compute an approximation or an enclosure after this time step, which also accounts for this quadratic error that we've attained. And this basically happens by just by looking at the exact constants of this quadratic O term and adding it as an uncertainty to the originally computed set. And so one can prove that the solution, starting from some initial set, is actually contained in the output of this set-based algorithm. Now here, so to illustrate, I use the Euler method, which has a quadratic error, but often one wants to be a bit more precise, and that's why we also formalized approximation schemes with a higher order of convergence. So for Runge-Kutta methods, the idea is that you nest the evaluations of the right-hand side of the ODE in such a way that the Taylor series expansions match up to a higher order. So, for example, the method of Hoyne, we evaluate the right-hand side once at the initial value, and we evaluate the right-hand side once again at the result of the first Euler step, and this way their remains just a cubic error. I explained that we use the idea is to have a set-based algorithm, and therefore we need some data structure to represent those sets. Why? Yeah, to enclose the errors that are attained just from the algorithmic, from the discretization due to the Euler or Runge-Kutta method, or because we calculate with finite precision, and then we want to account for the errors, for the round-off errors also in the set-based representation. First approach would be to use intervals or work with interval arithmetic, but as we've often seen this week, there's several problems. So you lose dependency between variables, and if, for example, the dynamics of the ODE rotates boxes which are wrapped again, you make overestimations which you just don't want to have. So we are going to work with affine arithmetic, which you've also seen up to now several times. The nice thing is that linear operations basically just distribute over the generators of an affine form. So all linear operations can be represented exactly. If you have nonlinear operations, you do a linearization of the nonlinear operation and account for the quadratic error with some additional noise term epsilon. And I should say that for the when we do the formalization and when we verify operations on affine forms, all operations are at first specified exactly. So they are specified on real numbers. So when we perform this linear operation, for example, there are no round-off errors or anything. To account for that, we introduce an explicit round-off operation, which can be, so in the logic, it will be executed, or it will be applied to after the exact operation. So first exact operation, then a rounding operation. And that makes the verification quite easy because it's a separation of different concerns. And as soon as we generate code, we can mix the two operations together, such that we have one operation which works with finite precision. And so how this refinement works, to now I've presented a more abstract specification of ODEs and the algorithms. That means in terms of real numbers, vectors of real numbers. And those are, of course, not computable, cannot directly compute with them. So we refine them towards data structures which are executable. So, for example, whenever we have a real number in our algorithm, we refine them to something I call software floating point numbers. They are given by a pair of mantissa and exponent, which are arbitrary precision integers. And the real number, which is represented by such a software floating point number, is just mantissa times 2 to that exponent. And so on those software floating point numbers, we can define round-off operations to reduce the length of the mantissa. And so we can also do that explicitly, which makes proofs easier. And what's important here is that when you have operations on the real numbers, like for example multiplication, if you multiply two real numbers which are represented by software floating point numbers, then you get again a real number which you can represent in terms of such a floating point number. Other refinements don't use sets but lists for the code. And if we have sets of real numbers, that means the enclosures that I talked about for the solution, those are represented by affine forms. And also so for many algorithms, it doesn't really matter how the enclosure is computed. So for proving interesting properties, it's often enough to just specify here at this part in the code, I want to have an enclosure of the solution. And then when you generate the code, you can use, for this enclosure, you can use whatever algorithm you like, the Euler method or Runge-Kutta method. So that gives you some flexibility. And after having refined the abstract specification towards something that uses only executable data structures, we use Isabelle's code generation facility and export code from the executable specifications. And so what do I mean by in principle generic? That this refinement approach that we implement real numbers by floating point numbers or enclosures with the Euler method or Runge-Kutta method, that allows to exchange in a modular fashion parts of the implementation that we get after code generation. So one could think of, for example, using not affine forms to represent sets, but Taylor models, once somebody has formalized Taylor models in Isabelle. Or one could use different approximation schemes for enclosures of solutions. So that gives some flexibility and modularity to the whole approach. Now, I think is a good point to make a short intermediate summary of what I've presented up to now and what we have verified and formalized in Isabelle. So we have a notion of the flow of an ODE, the solution which is unique. Then we have Runge-Kutta methods, which are based on, which use enclosures, which are set-based Runge-Kutta methods. And so the idea of using affine arithmetic together with classical numerical algorithms has or came from Buissou and others. And so, yes, the idea is to have a method which operates on sets and which is an enclosure for the initial value and returns an enclosure for the solution after some time. And this comes together with a formally verified guarantee that the set-based method is an over-approximation to the solution. And we use algorithmic refinement to obtain from this abstract set-based Runge-Kutta method something which is executable and works on floating point numbers, and for which we therefore can extract code. Now, I'd like to show how we use this executable Runge-Kutta method to obtain some useful results on concrete ODEs. First example is the oil reservoir problem taken from the literature. It models somehow an oil reservoir, might be, I don't know, pressure or whatnot, I don't know. It's important to note that this is a stiff ODE because at some parts in the state space you need very small step sizes. And this is because you have large variations in the right-hand side of the ODE. So that's the vector field, and here you see it points upwards and there downwards. So in between there, it's very you need to be very careful how to approximate the solution. And so this blue area that you see is an enclosure for the solution which has been computed with the verified tool. So it's basically, you can think of it as a mathematical proof that the solution is actually enclosed in there. And also, so the exported code is, I would say, reasonably efficient. So it's about 20 times slower than the comparable algorithm, the original algorithm by Buissou and others. That one is implemented in OCaml. We export code to standard ML, so it's both functional programming languages with some overhead. And so this 20 times more overhead comes just from the fact that, so first from the fact that we don't use IEEE floating point numbers, and also because the generated code is not really optimized. It's easier to, so there's simply a bit more overhead. And another thing to note, so this this problem here is it's a non-trivial problem. So some existing tools for guaranteed solutions, or for guaranteed enclosures of solutions to ODEs, fail to compute useful enclosures on this problem. But still, we can handle this non-trivial problem. There exist many more problems which cannot be dealt with this standard approach that I presented up to now. And this is due to several problems. So one problem is that zonotopes, so the sets which are represented by affine forms, so basically the enclosures that we encounter during the execution of our algorithm, they are always convex sets. And therefore, when in the real evaluation some non-convex set would occur, there occurs some wrapping. For example, if we have this non-convex set, a zonotope, any convex enclosure makes some over-approximation, which might explode when iterating the process. So first, very naive solution is to use splitting. Means if, say, the ODE or the dynamics of the ODE maps such a rectangle to this non-convex set, and we need to enclose this again in a zonotope, then we make an error. But if we split the set before this non-convexity occurs, then the enclosures for the resulting sets might be or the union thereof might be a better approximation. And the splitting is basically just heuristically guided. So one question is, how do you split such a zonotope? And when do you split? Because you don't want to split always, then you get an exponential blow up in the number of enclosures that you have to track during the approximation. So currently the heuristic is to split whenever a set gets too large. And so just using the splitting is, as I said, it's a bit too naive, because in the process there might just be exponentially many sets that you have to track in the meantime. So that doesn't scale very well. So one means that helps alleviating that problem is to try to reduce the size of the enclosures during computation of enclosures. And how can that be done? So one example is shown here. Say we have some enclosure, some reachable set at some point, and the dynamics moves that enclosure through, say, some hyperplane H. Then we can take the enclosure of the whole movement and compute the intersection of that enclosure with the hyperplane, and the intersection, that green set here, might be much smaller than the resulting set after this propagation. And even if it's not directly smaller, it might be beneficial that that it's basically flat in one dimension along the hyperplane. So that also often helps. And so what one needs to do to perform this kind of reduction is needs to compute the intersection of zonotopes with hyperplanes. And here first I wanted to show how this reduction is helpful at a concrete example. So that's reachable sets for the Van-der-Pol system. Starting from some initial set, x0, the dynamics moves downwards, and then here happens a first reduction, which is not too effective at that state. But you can see that here in continuing from here, the set gets stretched to the top left and down right, and so it gets larger and larger. Here you see the algorithm starts splitting up those sets because they get too large, and the next reduction happens here. It means all these reachable sets, which may be large or many, pass through just a small line here, so we can collect all parts of the solution at that point and just continue with this line, and that helps greatly in propagating the solution for a whole round, and this way you can finally prove that there exists something like a stable limit cycle for the for this Van-der-Pol system, because we return within the initial set.
So every time we see any irregularity in the drawing, there is something like that happen?
Yes, so here's a reduction, here's a reduction, here's a reduction, here's a reduction, there are several reductions. Just so when and where reductions happen, that's basically heuristically guided, and one could optimize that probably. That's an example of another ODE, the Lorenz equations. There, so say this is an initial set on top, and there the dynamics of the system stretches the solution very extremely to the left and right in the x direction. So we get very large sets here, and then in this black blob you see that the algorithm tries to compensate for this enlargement of the sets by just subdividing them, and finally they all pass through this point in the state space where a reduction happens, and then we have a relatively small set, and that can be propagated much easier than this huge amount of garbage there. And so I was inspired by Sylvie to open up a parenthesis here, because I want to talk a bit about verifying geometric algorithms, because the basis of this approach, reducing at hyperplanes, it's a geometric problem. So the reachable sets that we have are zonotopes, they come from the affine forms, and we want to compute the intersection with hyperplanes in general. So yes, a zonotope, that's the geometric interpretation of an affine form, and you can think of it as being generated as the sum of the line segments which are given by the generators in both directions. And so computing the intersection of a sonotope with a hyperplane, it's a relatively hard problem, and therefore Girard and Guernic invented an approximate version, which is computes an approximative intersection of a sonotope with a hyperplane. In their paper, the proof that this algorithm is correct, it's not at all formal. There's probably not even really a proof. It's just, if you look at the geometric problem, it's obvious that the algorithm is correct, but proving it formally is a different story. But the good thing is that this algorithm, the basic idea is quite similar to convex Hull computations, which have been studied by Knuth a long time ago, who gave a formal system how one can, more or less algebraically reason about geometric problems or geometric algorithms. So how does the algorithm work? First of all, the problem is reduced to a two-dimensional problem, to the intersection of a two-dimensional sonotope with a line. This reduction is done in the paper with such a proof, quite verbose. Proving this reduction in Isabelle goes automatically. So here we see this part can be done very easily in a proof assistant, whereas the geometric intuition is much harder to grasp for a proof assistant. So how does the algorithm actually work? So we want to compute the hull of a two-dimensional sonotope, and this can be done by taking the line segments, which are given by the generators, and appending them sorted according to their orientation. And then if we want to intersect this sonotope with that line, we just need to take the minimum and maximum point where the line intersects the segments. And okay, one difficulty here is talking about how are these line segments sorted in the two-dimensional space. And this is done quite nicely and abstractly by Knuth, who invented the theory of counterclockwise systems. There you basically have a ternary predicate which talks about orientation of points in the plane. So here we have P, Q, and R, and P, Q, R are related in this predicate because from P over Q to R we take a counterclockwise turn. And then Knuth defined some axioms which need to hold for such a counterclockwise predicate. And it turns out that this set of axioms suffices to do many proofs about algorithms which involve points in the plane. So you never really have to go down to the coordinates of the points. You can just reason with this abstract predicate. And the axioms that need to hold is, so we need to have cyclic symmetry. If PQR holds, if PQR are counterclockwise, then QRP is counterclockwise. If PQR is counterclockwise, then PRQ cannot be counterclockwise. 3 points always need to be in some orientation. And if we have points oriented like this, T, P, and Q, and T, QR, and TRP. So T is in the middle of R, P, and Q. Then we can also get an orientation for the outside points of the triangles. And most importantly is transitivity. So we assume that we have 2 points T and S, and that P, Q, and R are 3 points which are counterclockwise. That means left of or on top of this line. And then if we have, if Q is left of P and R is left of Q, then we can also perform this transitive step that R is left of P. And so this gives us something like a total order in the half plane left of TS, and that allows to talk about sortedness and is basically the basis for the correctness proof of the algorithm. In our case, we needed to extend this abstract theory a bit more to also work for vector spaces and not just discrete points in a plane, to be able to translate this predicate to scale it a bit, or just to reflect and add some of the points. So it was just short excursion to verification of geometric algorithms. And I think the take-home message there is that once you find the right level of abstraction, you can do proofs relatively elegant, also in a proof assistant, in application areas where you wouldn't really expect it. So for geometric algorithms, it's something we think it's we need to appeal much to intuition. So last point, said already in the beginning, like the most important application of these verified ODE solvers is the Lorenz Attractor. It's about the Lorenz Attractor, which arises from a set of equations that have been introduced by Edward Lorenz in 1963 to model more or less flows in the atmosphere. So modeling weather in some sense. If you simulate that system numerically, you observe that all solutions tend to such a structure, which is called the Lorenz Attractor. And the interesting part about this attractor is that, as I said, all solutions tend towards this attractor. But if you have two solutions on that structure, no matter how close they are, eventually they will diverge again. So that's what's called or what has been coined as a butterfly effect. And that's, you can also say that there is chaos in the attractor, or one says that the Lorenz attractor is a strange attractor. This has only been conjectured for quite some time because no one has been able to prove it. And that's why Stephen Smale put it on a list of 14 problems and of more problems for the 21st century. And the problem didn't even make it to the 21st century because Warwick Tucker managed to prove it in 1999 with a curious combination of analytical reasoning for some parts of the attractor, but also numerical approximations on other parts of the attractor. And so his proof basically relies on the correctness of the C++ program that he wrote for this purpose. And you can ask yourself if you want to trust that C++ program or not. And the thing is, what this program does is it computes an enclosure for the Lorenz ODE. And that's basically what our verified ODE solver can do. So the idea was to apply the verified ODE solver to the Lorenz equations. And here's the context of this application. So how does the proof work? It basically consists of three parts. So the first part is to compute what I call an attracting set. This requires a numerical enclosure for the ODE. Second part is in that attracting set, one needs to prove that there is a sensitive dependence on initial conditions. What I said earlier, that no matter how close solutions are, that at some point they will diverge. So the first point can be done with our ODE solver. The second point should be feasible as well. And then there's a huge part of analytical reasoning where this numerical approach does not or even cannot work. And so the contribution that I'm presenting here, this application, is basically the verification of such an attracting set computed with the verified ODE solver. So what's the attracting set? So the standard approach is, or when studying chaos for this attractor, is to reduce this three-dimensional dynamics to a discrete dynamics on a two-dimensional plane, on this return plane sigma, and then look at iterations of a map of what I call the return map on that return plane. This return map is defined as, for some point x, as the point where the solution first returns back to that plane. That's the return map. And so basically what Tucker did was to compute numerical enclosures for the solution to obtain an enclosure for the return map. And that's basically what we can do as well. And then we need to certify that there is something like an attracting set. That means a subset of this return plane here, where once you are in that set, you won't leave that set again. So that's the attracting set. If you return from this attracting set, you end up in the attracting set again. This is a problem which is luckily easily parallelizable. So we subdivided this candidate for the attracting set into 14,000 smaller ones. And that's essentially what Tucker did as well. So he also used a massively parallel computation. And then we can compute for each of those small sets independently that the return is included in the attracting set. And this took on 1,000 CPU cores, 5 hours each, so 5,000 CPU hours roughly. And Tucker at the time, like almost 20 years ago, his computations took 2,000 hours. So that's also more or less in the in a reasonable relation. And so, yes, as a result, we verified an attracting set which is sufficiently precise for the remainder of Tucker's proof. So here you see, so the blue set is the one that has been used by Tucker in his proof. The black one in between is the one that we verified using Isabelle. And in the course, so to come up with this, with the attracting set on the return plane, we need to, of course, enclose the HOL attractor. And that's what you see here. So the Lorenz Attractor, or a verified enclosure for the Lorenz Attractor from the front, from the left, and from the bottom. So I'd like to conclude by saying that verification of such rigorous numerical algorithms is feasible. It's both feasible and useful. Useful because we can now have a verified computation as part of a proof. Useful also because we can compute some non-trivial examples. And feasible because in some sense this combination of affine arithmetic and Runge-Kutta methods, this has been done by Buissou. Combining it with this reduction method is also for in the context of hybrid systems or continuous systems reachability analysis has been a novel algorithm, and even such things can be verified in a theorem prover. So that's it. Thank you.
Thank you. We have time for maybe 2 questions.
Do you have any ideas for doing stiff systems apart from just doing very small time steps? So things like trying to formalize implicit solvers or rigorize them?
Not really, yes. So the first idea would be to formalize implicit solvers, but I have no idea if or how that can be done rigorously. It could be done? Okay.
Thank you. This is, really impressive that you've managed to do this. We've tried an ODE solver in Coq, and we only got, a small amount of what you've done. And actually, tackling this problem that was open for quite a long time. It's really nice work.
Thank you.
So my question is about the extraction. So what guarantees do you get about the code in Isabelle? And so did you actually prove the whole Lorenz Attractor that it's chaotic, also the analytic part of only the ODE solver?
Okay, so first part of the question, what do you need to trust?
Yes.
So you need to trust that the formalization of what we consider to be an ODE or a solution of an ODE is correct. And apart from that, you only need to trust in the code generation, the mapping from the executable specification in Isabelle to an SML program. But so that's more or less a textual translation. So all this refinement from real numbers to floating point numbers and these round-off errors, this all happens inside the logic. So that's verified. What was the second part of the question? Oh,
did you verify the analytic part?
No. That's 60 or 70 pages of Tucker's PhD thesis. So that's a larger effort.
Okay, thanks.